Hello students, this is your how-to video for your week 8 critical analogy equilibrium assignment. You'll notice I have that pulled up on the screen right now. The only thing it's missing is the video because I am creating it. Please remember that with the critical assignments, all 4 assignments must be completed. You must also earn at least 60% or higher on each individual critical assignment in order for them to count towards your passing grade. Now please remember again that it doesn't matter if you get 80% in the class if you don't complete the critical assignments. So the critical assignments must all be done, meeting the requirements, and you must have an overall grade of 60% or higher to pass the course. Now, in order to access your critical analogy assignment, you're going to click on this link right here, and that's going to open up into a OneDrive document like this. Now when you look at this, it's going to have some background information. I highly recommend that you read the background information because it's going to give you definitions and talk about the things you're going to see within the table itself. So this is going to have all the little pre-knowledge and review that you're going to need in order to be successful. So make sure you read that first page. And then it has the directions right here. So you're going to have reactions from the human body. You're going to have an analogy that's already given to you. And that's going to be one I talk about within this video. And then analogy number 2 is going to be the one that you make up. So those are the 3 things you're going to see. And then you're going to see this table right here. Okay? This is the table that you're going to complete. Now I'm going to walk through how to do analogy number 1, the escalator. And I'm going to go through and kind of help guide you on the thought process you're going to need to have in order to make sure that this goes smoothly, quickly, and so you don't have a whole lot of questions. Now the analogy itself is going to look at an escalator. So you see this picture right here. And with my picture, I have an escalator that goes up. I also have one that goes down. On the left side, I only have people going upwards. On the right side, I have people going up and down the escalator. So when I look at that in terms of this table, the first one says summarize the reaction. So summarize this analogy in everyday terms. In this, I would simply say that I have people that are going up and down an escalator. That's all I would have to say. Okay, so it's just a basic summary of what you're looking at or what your analogy is. The next step would be temperature changes. And it says, how would increasing temperature, in quotes, be shown in this analogy? How would decreasing temperature be shown in this analogy? And then what about collisions? So with this one, we're not going to necessarily have collisions, but we can talk about temperature. And for me, increasing temperature would be increasing possibly the energy at which the people on the escalator have. So my example of that would be, instead of people standing on the escalator, we could have people actually running up the escalator and running down it. The people have more energy, they're moving faster, and that's going to cause them to potentially have more collisions. So that's my analogy in terms of the temperature change. The next piece would be surface area. How would increasing surface area be shown in this analogy, and how would decreasing surface area be shown in this analogy? And then what about collisions? So my thought process for surface area when it comes to an escalator would simply be to make the escalator wider. What if we had a wider escalator? You have more chances or more area that you could have people fit on it, and therefore that's going to increase how many people can go up and down at the same time. And thus that would ultimately increase collisions if we're talking about people bumping into each other, possibly. So that was my thought process on surface area change. The next one is concentration changes. How would increasing reactant concentration be shown in this analogy, and how would decreasing reactant concentration be shown in this analogy? And then what about collisions? So this one, I would say we're talking about one side of the escalator. So if you have people going up the escalator, and let's say that's my reactants, if I have far more people wedged into a smaller space, I'm increasing my concentration. If I have less people within that side of the escalator, that would be decreasing concentration. If I have more people on the escalator, you have more chance of people bumping into each other and having more collisions than if I didn't have that many people on there to begin with. Next one is catalyst. How would a catalyst be if we added a catalyst? What might that look like? So this one's a little bit trickier. Now, if we're talking about a catalyst, we could talk about maybe instead of having stairs on an escalator, maybe it could be a flat ramp. And that would make it easier for people to get on and off versus having just a simple level to be on. Now, again, this has a wide range of what could potentially be added or taken away. Just try to use your best judgment when it comes to talking or thinking about how this would apply. The next one is incomplete reaction, and the definition for that is a chemical reaction that doesn't run to completion. So meaning we can have reactants going to products, but we can also have reactants still be present in the same container. So what that means is if I have an incomplete reaction, I still have people that are going to be on one side versus the other within my analogy, because not everybody's going to be on the same level. So if an escalator is going to bring people from one level to a higher level within, let's say, a mall, okay? Let's say we're talking about a shopping mall. My reactants are going to be the first floor individuals, and my products are going to be the second floor individuals. Now, I will still have people on the first floor, even though I have individuals going up the escalator onto the second level. So it's never going to be complete. I'm never going to have all these people going up to the second level and not have anybody on the first level. So that's going to be my analogy in terms of an incomplete reaction. Next is closed system. No reactants or products are entering or leaving the container. So this would be an example if we were to put, let's say, the mall on lockdown. Let's say the mall had locked doors, nobody could go in and out of the building. That would be considered a closed system because you have nobody leaving and nobody coming in that's new. Now, in reality, the mall is not going to be a closed system. So I could say this really isn't an analogy of a closed system unless I were to do this. So if I lock the doors, you can't have anybody new coming in or out. Okay. Next one is reversible reaction, meaning the forward and reverse processes are happening at the same time. And I can see that when I'm dealing with an escalator because I have one going up and one going down. Again, if my first level is my reactants and my second level is my products, I have people going up towards products and people going back towards reactants. So I do have a reverse reaction taking place within that analogy. The next three kind of go hand in hand. Do I have equal rates of forward and reverse reactions? Do I have a constancy of properties, meaning there is no net change in the amount of reactants or products? And the dynamic process, the system is changing continuously, but the forward and reverse changes happening at the same rate cancel each other out. So dynamic means moving, if we're talking about the last one first. You have a dynamic process that's constantly moving. However, I still have those equal rates moving forward and backward. So that means my rates of people going up and down are going to stay the same. And again, remember, rates are having to do with the speed of the reaction itself. So those rates are staying the same. Now, if I have a constancy of properties, that means there's no net change in the amounts of reactants or products. So in this case, I'm not going to have a change when it comes to the individuals on the second and then the first level. Okay? So even if I have people going up and down, I'm still not going to have that change because my rates are going to be the same when it comes to people going up and people coming down. And then again, dynamic means it's constantly moving. So that's the example of the middle analogy here. And you can fill those out as you are listening to the video. You're going to, again, have an example reaction from the body, and that's going to be a little bit easier because that's actually following the layout of your chemical equation and what we're really applying that to in chemistry. And then analogy number 2 is something that you're going to make up. Now, the only other analogy I don't allow students to use is an elevator because it's too similar to an escalator. So make sure that when you're thinking of an analogy that you come up with one that's not an escalator and not an elevator. And then you have to have a different one if you have a sibling or friend in the course. If you get stuck on anything or you need help, be sure to reach out. Otherwise, good luck on your critical assignment in week 8.